This is the 33rd session on relative velocity. So in this session, I'll take up one more problem on shortest distance calculation between two moving points when A relative is 0, as mentioned in the importance of this as mentioned in the previous video. Okay, I'll write down the question. Fine. So the question is this: S1 and S2 are two shells. S1 and S2 are two shells thrown simultaneously in Earth's uniform gravitational field. Earth's uniform gravitational field from the top of two towers T1 and T2 with respective speeds as shown. And 14 meter per second as shown. These are the two towers T1 and T2. Vertical separation between these two towers is 22 meter and the height difference between the two towers is 9 meter. A shell S1 is thrown here and shell S2 is thrown here simultaneously in Earth's uniform gravitational field at an angle of 45 degree. This is also at an angle of 45 degree. Initial speed of S2 is 14 meter per second. Initial speed of S1 is 2 meter per second with respect to ground. Only height difference between two towers has been specified, not the actual height of the two towers. Okay, but they are tall towers. Now, question is to find the shortest distance between these two shells in course of their motion. Again, we have to assume ideal case. We have to assume only that acceleration of both the shells are equal to g, downward direction, and there is no effect of air resistance, there is no effect of Earth's rotation, etc., etc. Only ideal case we are taking. Okay, so this is the situation. Fine. So first of all, we have to check whether A relative is 0 or not. So for that we write this: as2 s1g, relative acceleration of s2 with respect to s1 in ground frame, that is just equal to a2g minus a1g, that is just equal to a2g plus, that is just equal to, now a2g is the acceleration of s2 with respect to ground, that is vector g, ideal conditions, minus a1g, that is also g, that is 0 for all times. This 0 meaning this s2 s1g we are denoting it by a relative. Okay, this is 0 for all times. This means relative velocity is constant between these two shells, and then because it is constant, this is the same as the relative velocity at time 0, that is u relative. And one more thing, since relative velocity is constant, this means that as seen from s1, s2 will be moving in a straight line at a constant speed, or as seen from s2, s1 will be moving along a straight line at a constant speed. Fine. So now we can, since a relative is 0, so we use this relative velocity method to solve the problem. Okay. So we solve either we are seen from S1 or seen from S2. We solve the problem as seen from S1. So solved as seen from S1. Solved as seen from where? S1. Okay. This I'll grab it. Okay. So now again we can solve this problem in two ways. One is by resolving the relative velocity in two components, or by direct without resolution. Both ways we can solve. Okay. So what I'll do is that I'll just rub it. Okay. So this I made it clear that as seen from S1, S2 will moving along a straight path at a constant speed, and that is same as relative velocity at time 0, because relative velocity is constant. Okay. I redraw this diagram. Okay. I redraw this diagram. Okay, fine. So the diagram is this. So problem solved as seen from S1. As seen from S1. So what we have to first do is that we have to first find U relative. U relative is the initial relative velocity of S2 with respect to S1. That is just U2g minus U1g. That is just U2g plus reverse of U1g. So here I am solving the problem without resolution. Okay, without breaking into xy component directly. Okay, I'll also solve the problem with resolution after this. Okay. So this is the initial relative velocity, and this is also the relative velocity at all other instants, because relative velocity is constant. So I'll draw the diagram here. Okay. From here, S2 has been fired 14 meter per second at an angle of 45 degree. S1 has been fired at 2 meter per second, that also at 45 degree. This is S1, this is S2. We are solving as seen from S1, so we are observing S2 from S1. So to find U relative, we have to reverse this and add to this. This is this way reverse. If we reverse it will be like this. 2 meter per second is 45. This is also a 45 degree. Is also given to a 45 degree. So U relative is the vector sum of these two. Vector sum, Lagrange law of vector addition. I'll just redraw it again. I'll redraw it again slightly. Diagram is not proper. Like this, okay? This is 45 degree as mentioned just now. This reverse this 2 meter per second. This is also 45 degree. This is also 45 degree. Okay. Combine these two. This is U relative. Now this is also the relative velocity at all instants. So as seen from S1, S2 will move along this path, straight path, at a constant relative speed of U relative. As seen from S1 is at its own location. S2 is moving like this along a straight path at a constant relative speed of U relative. The shortest distance between S1 and S2 will be the normal distance from S1 on line of motion of S2 with respect to S1. So this is the shortest distance, R minimum. Okay, this is the shortest distance between these two moving points, shells. Okay. Now we have to find this R minimum. For that, what we do is join these two lines. Let this line be L. L can be found from the geometry of the situation. This is 22 meter and the height difference is 9 meter. This is equal to 9 meter. This is 22 meter. This is equal to L by Pythagoras theorem. L will be 22 square plus 9 square. That is just root 565 meter is the value of L. Root 565 meter is the value of L. Now we have to find this. So what we do now, we assume that this angle to be theta. We assume this angle to be phi. We assume this angle to be psi. So in this right angle triangle, R minimum by L equal to sine of psi. In this right angle triangle, okay. What do we write? R minimum by L equal to sine of psi. Now psi can be seen to be theta minus phi minus this. This plus this angle is equal to theta from geometry. You can see it. Theta, total angle theta is equal to psi plus this angle phi plus this angle 45 degree. So psi will be written as theta minus phi minus 45 degree. We substitute psi here. So this will be sine of theta minus phi minus 45 degree. Okay. Now this will break by sin A minus B rule. So this is just equal to sine theta minus phi cos 45 degree minus cos theta minus phi sine 45 degree. So this is equal to 1 by root 2 sine theta minus phi minus cos theta minus what? Phi. Now we have to find this L, we have already found out. Now we have determined these two, sine theta minus phi and cos theta minus phi. Now tan phi, you can see it is 9 by 22. See, this is 9, this is 22, right angle triangle, this right angle here. So tan phi is equal to 9 by 22. Fine. What about tan theta? Tan theta is equal to this by this by this. This is 14, this is 2, this is also 2. So theta, this is also theta, alternate angles. So tan theta is equal to 14 by 2. 14 by 2, that is equal to 7. Okay. So tan theta is equal to 7, tan phi is equal to 9 by 22. Now we have to determine sin theta minus phi and cos theta minus phi. For that, it will be better if we find tan theta minus phi, from that we can determine these two. Alright. So tan theta minus phi from geometry is same as tan theta minus tan phi by 1 plus tan theta tan phi. We can write it this way. So tan theta is how much? 7. Tan phi is how much? 9 by 22. 1 plus 63 by 22. So this becomes 145 by, this will be 154 minus 9, 145 by 85. This becomes 29 by 17. So tan theta minus phi is this much. But we have to determine sin theta minus phi. From trigonometry, that will be 29 by root under 17 square plus 29 square. That is seen to be root under 1130. And what about cos theta minus phi? Because tan theta minus phi is known. So cos theta minus phi will be 17 by root under 17 square plus 29 square. That is just equal to 17 by root 1130. We have obtained all these values. This is substitute here in this one. So R minimum will be L by root 2 sin theta minus phi minus cos theta minus phi. How much is sin theta minus phi? 29 by root 1130 minus 17 by root under 1130. This will be L is equal to root 565 as we have seen just now by root 2. 29 minus 17 is 12. Root 1130 is root 2 into root 565. These two cancels out. 12 by 2. This becomes equal to 6 meter. This is the answer. In method 1 we have obtained the answer. In method 1 we see that the shortest distance between the two shells in course of their motion is 6 meter. Fine. So this one, method 1, I have solved by without resolution. In this you see, without resolution, when it has been solved, it is slightly complicated. A lot of calculation has to be done. So in this case it is better sometimes to resolve also we can do. That was I have demonstrated. Okay. So I will just rub it. Okay. Fine. Now I'll solve this problem by method 2, by resolution method, okay? By resolution method. Again we are observing the problem of S1. S2 observed from S1. S2 observed from where? S1. So again draw the diagram. See, velocity of S2 is 14 meter per second, 45 degree angle. As seen from S1, we reverse this, 2 meter per second, 45 degree. The relative speed becomes this much. This is U relative, okay? It makes some angle alpha, say, with the horizontal. This is U relative. This I extend it further. I join these two. This is L, as has been found out. You drop normal here. Alright. This angle we determined by what? Theta, just now. Tan theta 9 by 22. 9 by 22. This is alpha. This is R minimum, shortest distance, as you just now discussed, okay? And this is L. This is right angle triangle. This by this equal to sine of alpha minus theta. R mean equal to L sine alpha minus theta. Tan theta is this much. Only we have to find alpha. So how to find tan alpha? That is the question. Now what we do, we resolve. U relative has a component along leftward. Let's call leftward direction as x-axis. Let's call this as y-axis. So U relative x is the sum of x components of these two. They are the same direction. 14 cos 45 degree. 14 cos 45 degree. 14 by root 2 plus 2 cos 45 degree. 2 by root 2. 16 by root 2. It is 8 root 2 meter per second. What about U relative y? Upward direction is y-axis. That is equal to 14 sin 45 degree minus 2 sin 45 degree, because they are in opposite directions. So 14 by root 2 minus 2 by root 2. That is just equal to 12 by root 2. That is 6 root 2 meter per second. Now this is U relative y, this is U relative x. So tan alpha is equal to U relative y by U relative x. U relative y is 6 root 2 and U relative x is 8 root 2. That is just 3 by 4. Okay, tan alpha is this much and tan theta is this much. Now we have to find sin alpha minus theta. And L we know, L we have already found in method 1. Root 565 meter. That is L. Okay. Now we substitute in this one. So R minimum will be, L is root 565 sin alpha cos theta minus cos alpha into sin theta. That is just root 565 sin alpha. Tan alpha is 3 by 4. By trigonometry, sin alpha will be 3 by 5 and cos alpha will be, I'll drop it, okay. Sin alpha will be 3 by 5 and cos alpha will be 4 by 5. So sin alpha becomes 3 by 5 into cos theta. Tan theta is this much. From this we see that cos theta will be how much? 22 by root 565 and sin theta will be how much? 9 by root 565. Substitute both of them here. Cos theta is what? 22 by root 565 minus cos alpha. Cos alpha is how much? 4 by 5 into sin theta. 9 by what? Root 565. Okay, root 565 goes away. Okay. Okay, so how much will this be? 22 into 3, 66 minus 9 to 4, 36 by 5 into 66 minus 36 by 5. Okay, fine. So 30 by 5, that is 6 meters. Same answer I obtained again. Fine. So in this way, in this 33rd session of relative velocity, the shortest distance between two moving points has been determined by both the methods. Okay. So till here we have just completed the relative velocity shortest distance problems. Okay, this is finished here. So next video I will take up the relative velocity collision problems in 2 dimension. That will also be done in 2 phases. Phase 1, phase 2. Phase 1 in which relative acceleration is 0, and phase 2 in which relative acceleration is non-zero. That will take up in the next video. Okay, I'll close it here itself. Okay, fine.